In this video, we're going to be diving deeper into second-order systems, which take the form x double dot plus 2 zeta omega n x dot plus omega n squared x equals 0, and their solutions. Um, so we'll recall that zeta is the damping ratio of the system, and omega n is the natural frequency of the system. So the damping ratio and the natural frequency have physical meaning. The damping ratio is a measure of how quickly the solution decays. And the natural frequency tells us the speed of response. Um, so it's it's a frequency. It tells us um, how quickly the system is maybe going to oscillate, or maybe come to zero, or come to some steady state solution if there's no oscillation. We also have what's called the damped natural frequency, omega d, and this is an actual physical measure. If we have um, if we do have oscillation, then this is a measure of the actual frequency that you can measure. Um, and omega d is equal to, by definition, um, natural frequency times the square root of 1 minus zeta squared. And the solution to these differential equations, or to these second order systems, is x equals c1 e to the p1t plus c2 e to the p2t, where p1 and p2 equal minus zeta omega n plus or minus um, I times omega d. Um, and we can, based on what zeta is, based on um, the physical uh, parameters of these systems, we can actually go ahead and come out with an automatic solution for some of these. So I'll go ahead and post this picture in here of what the solutions look like. So you can see in this top row, if zeta equals 0, then it's undamped. You can see the picture of the solution there. It looks kind of like a sine wave. And the solution simplifies to a sine plus a cosine. If in the second row the solution is underdamped, in the second column we can see what P1 and P2 are, and you can see that there is some oscillation, but the system decays as a measure um, of zeta, or as in relation to zeta. If zeta equals 1, the system is critically damped, and the system decays as fast as possible without any overshoot, without going past its final value. Um, and you can see the values there. This is on a table in the book. In the edition that I'm looking at, it's page 30, might be page 32. Um, but if it's overdamped, then the system goes a little slower to zero without any overshoot. And then if zeta is less than 0, or if it's imaginary, you have an unstable system. Rather than exponential decay, you have exponential growth. Um, and we can get in the case of the undamped and underdamped solutions, the sines and cosines, remember we're looking at a system that's x equals c1 e to the p1t plus c2 e to the p2t. We can get sines and cosines out of that from Euler's formula. And Euler's formula is that e to the I theta, or e to something times the imaginary number I, equals cosine of theta plus I sine theta. And you should memorize this. This is quite important. So if P1 and P2, you can see that here there is a possibility for some imaginary component. And if there is an imaginary component, that will cause us to have sines and cosines. We can substitute e to the I theta for sines and cosines. And so we'll do a couple examples here just by exponentiation rules. If you have e to the a plus I theta, so if your pole is negative zeta omega n plus or minus I omega d, so you've got theta in the omega d slot, then that equals e to the a times e to the I theta, which equals e to the a times cosine of theta plus I sine theta. The same thing for if you have e to the a minus I theta, then you end up with a just a minus sign right here. Um, and it's this Euler's formula, this solution, this result right here that connects all of our different values of zeta and connects systems and allows us to use the same mathematical tools for systems that oscillate, systems that don't oscillate, and gives us this useful table of solutions right here.